In this lecture, we're going to look at more reactions of alkynes. And so we're going to start with the hydrogenation of alkynes. So, oops, well, sure, we'll make that big. Well, it would help if I spelled it right. Hydrogenation of alkynes. Okay, so for the hydrogenation of alkynes, what we're doing is taking our alkyne, we can have it unsubstituted or substituted on both sides. And it could be differentially substituted, so we put an R prime on one side. It doesn't matter. We're going to react this with hydrogen gas. And it's hard to use a gas in a reaction and not have it used in excess. That usually means we just add a bunch of it and see what happens, right? I mean, it's hard to add like 1 mole of gas. Okay, so if we have palladium on carbon, our usual catalyst for this type of reaction, what we're going to get is what's called exhaustive hydrogenation, where all of the pi bonds are converted into carbon-hydrogen sigma bonds. And so we could call this exhaustive hydrogenation. And so again, the alkyne is like 2 alkenes. Both of the extra bonds do a typical alkene reaction. In this case, it was hydrogenation, and we could use deuterium and tritium gas to accomplish the same thing. And again, this doesn't matter whether or not we have substituted on both sides, substituted on one side, we're going to get the alkane resulting from exhaustive hydrogenation, where we add hydrogens everywhere that was multiply bonded. Okay, so that is the hydrogenation. There's no way to kind of use this system, all of these reagents, and sort of do any further control on the reaction, stop halfway through. If we wanted to stop, we would do what's called a Lindler hydrogenation or a Lindler reaction. So this is called the Lindler reaction or the Lindler hydrogenation. And what we do here is we do a partial hydrogenation of an alkyne. And the way this works is we use our typical palladium catalyst, but we poison the palladium catalyst. And so the poisoned palladium catalyst is less reactive. So poisoned is in quotes, right? I mean, it's not like a living thing. It's just a metal atom that can facilitate the addition of hydrogen gas across a pi bond. And this catalyst is critical, otherwise this reaction is too slow to proceed. So it's poisoned, has been poisoned, is less reactive. Now what we can do is we can take advantage of the poor reactivity of this palladium catalyst and allow it to only react with one of the pi bonds of an alkyne. Recall that the third pi bond in an alkyne is weaker, and so it's still able to react with the poisoned palladium catalyst in this case. But after we do that, we form an alkene, and that alkene pi bond is too strong for our poisoned palladium catalyst to react. So with the poisoned palladium catalyst, the weaker third bond of an alkyne, and that's a pi bond, So the weaker third bond, which is a pi bond, there's not 3 pi bonds, there's 2 pi bonds. That's able to, that weaker bond is able to react with H2 gas, is able to still react with H2 gas. But, and here's the other point, the stronger pi bond, and you could think of that as the second bond of an alkyne, maybe, sure. I mean, the two are identical until one reacts. So both the pi bonds are pretty weak until a reaction occurs and forms an alkene. And then that remaining pi bond, if they only react one at a time, is stronger. Okay, becomes stronger. The stronger pi bond cannot react. With H2 and the poisoned catalyst. Okay, while you are writing that down, I'm just going to check my notes. I believe I know what the Lindler catalyst specifically is. It's not like a structure that you need to know, but I believe it's got quinoline added to it, which we could draw. Okay, so it's got some oh, yeah, it's got some quinoline, but it's got some lead added to it and then some calcium carbonate to it. So we could just make note of that. So it's, instead of palladium on carbon, it's palladium on calcium carbonate plus lead acetate plus a heterocycle, which is benzene fused to pyridine, and that's just quinoline. So if you mix these together, you get a palladium catalyst that is not as active as palladium on carbon is. It's still active enough to react with the third alkyne, or the third bond within an alkyne, the weakest bond, the weaker of the 2 pi bonds, but it's not able to form do an exhaustive hydrogenation. So you get a partial hydrogenation. Let's get into it. So what is the outcome here? Well, if we've got our differentially substituted molecule and we add H2, and I'm going to write over the arrow Lindler's catalyst, cat with a period, what we get is an alkene. But it's not just any alkene, it is a cis alkene. So only the cis alkene results. And cis is always Z. So we only get a cis alkene. Now you might be like, hey, Willoughby, you went to a big deal to say we should use E and Z. Why are you referring to cis? Well, I'm just taking advantage. We're always going to add 2 hydrogens to the molecule. I mean, I guess if it's deuterium, maybe it's not quite cis, even though it's an isotope. But because we're adding 2 hydrogens, we get into our cis-trans realm, and we only get cis. So why only cis? Well, this goes back to something that we talked about last time when we looked at the reaction of hydrogen with alkenes, and that is why only cis? The H2 is delivered syn. So we don't need to know the mechanism of this, but we need to know that the 2 hydrogen atoms are kind of added simultaneously to one side or the other, both on top, both on the bottom, but we can't go opposite sides. We can't go top and bottom. That's because in a metal catalyzed reaction, in this particular metal catalyzed reaction, the mechanism, which is beyond the scope of the course, does not allow it. And so you always get the cis alkene that results. So if we do a few examples, and this is just a topic, it's the same as what we talked about last time. But if we have this plus Lindler's catalyst, we would get this molecule, and sometimes with that linear structure, I need to make sure I count my carbons. 1, 2, 3, 4, 5. So one of the triple bonds converts into a double bond. We don't have to worry about exhaustive hydrogenation. Whereas if we had taken the exact same alkyne and reacted it with palladium on carbon, we would get this molecule resulting from exhaustive hydrogenation. Now, if we use Lindler's catalyst in the presence of a alkyne that's called terminal, that is, it's at the end of a chain, one side's hydrogen, the other side is the rest of the molecule, all of a sudden we don't have to worry about cis and drawing that cis product, because the cis product doesn't exist because there's two hydrogens on either side. So for this one, it's here is the product, but we already had a hydrogen present. And sure, I guess if we were isotopically labeling, then we would have to worry about it a little bit more. But the two hydrogens that come from the gas and are delivered by way of the metal that's been poisoned are, just like before, delivered syn, same face. You can be top or bottom just as long as you get to draw a cis product. Okay, so I'll do it for this lecture. We'll see you next time with more reactions of alkynes.